Okay, so this is chapter 1 of the second year A-level applied book for Edexcel, and for various reasons I happen to have access to a scanned copy but not the actual textbook, so hopefully you can still see this on the paper. Now we're looking at correlation, and the first thing to remind you of, although we're going to deal with section 1.1, I'm just going to look at these diagrams here on page 5, because these are the diagrams which we should remember with correlation. We can have a strong negative correlation, or in this case a perfect negative correlation, where the gradient of the line of best fit is negative, and if it was perfect the points would be exactly lined up on the line. Or I can have a negative correlation. This is quite a strong one, the points are quite close to the line. Zero correlation, the points are spread out all over the place. A positive correlation, and this would be a sort of, these points are supposed to be spread out a little bit more, they're not too close to the line, so that's a reasonable positive correlation, and this is a very strong, in fact this is a perfect positive correlation with the points exactly on the line. So that's the picture that we've got of correlation. We can have perfect negative correlation, we can have strong negative correlation, weak negative correlation, no correlation at all, weak positive correlation, strong positive correlation, and then perfect positive correlation. Okay. Now obviously if we're dealing with real life data, we're never really going to get a perfect correlation because real life data is always going to wobble around a little bit. But so far we've just been able to classify correlation as positive or negative, weak or strong. Okay. Now the whole point of this chapter is to get a little bit cleverer with correlation, and when we get to section 1.2 we're ignoring for a moment these numbers under here, but we'll talk about what those mean when we get to section 1.2. The important thing for section 1.1 is that this is our picture of correlation. It's all about straight lines. Okay, it's all about straight lines. Now, if I had two variables, let's call them x and y, and I measured the data, and I found that this is what happened, there is definitely a link there between x and y, isn't there? It looks like we've got some sort of parabola or some sort of U-shaped curve going on. But if I looked at whether there's a correlation, in maths, a correlation is a linear relationship. There is a line of best fit. So if I look for a correlation here, probably there'll be a positive correlation. We get a positive line of best fit, but it's not particularly strong. These points aren't particularly close to this line. So we've got a problem. In the real world, if you say there's a correlation between this and that, what you usually mean is that there is a link between this and that. Here, if I ask for whether there's a correlation between x and y, mathematically speaking, this is not a linear relationship, so it's not helpful, because we would say there's not really a correlation there. There is a relationship, but not a linear relationship. So what we're doing in section 1.1 is we're looking at a couple of examples of where we may have a relationship between two variables, which we're going to call x and y, and how we could use the tools of correlation to describe that relationship. So in the rest of the chapter we're going to go back to correlation. Here we're looking at what if they're non-linear relationships, how could we fiddle things around, because in section 1.2 and 1.3 we can test how strong the correlation is. We can test whether or not there is a correlation, and in section 1.3 we can do a significance test on whether there is a significant correlation. So if we've got those mathematical tools, we want to be able to use them in non-linear relationships as well. And those mathematical tools in section 1.2 and 1.3 work for linear relationships. So what can we do if we have something else? So the first example here is if you have two variables. So the way it would work is you would have imagine the sort of table. Now hopefully if you were doing the real statistics you would have too many numbers to put in a table like this, but this is the idea. You have a huge spreadsheet with massive columns x and y with hundreds of pieces of data in, but just imagine our normal sort of table with the x data here and the y data here. So I don't know, score in maths and score in physics or something like that. The usual sort of data that we'd record, bivariate data is the name for it, bivariate two variables. Okay, now what if the relationship between y and x is this kind of relationship? So this one in this example here, y equals a times x to the power of n. Okay, so it's some sort of polynomial relationship. X to the power of n could be x squared, could be x cubed, something like that. Now this is not going to have a correlation. It's not going to have a straight line relationship between the two variables. So what can we do? Well, if we look at this equation, if I take logs of both sides, I get log y equals log a x to the power of n. So that is log y equals, now using my log rules here, this is log a plus log x to the power of n, and then the n can come down at the front using the power rule for logs, log a plus n times log x, okay? Now if we look at that, if instead of log y, I just had a y, and instead of log x, I just had an x, what I've got here is a straight line, isn't it? Y equals something times x plus something. So this is, and log a, remember, is a constant. N, remember, is a constant because it was just this thing here. So this is something of the form y equals mx plus c, isn't it? So this thing is a straight line. So what we've got here is, if we have this kind of relationship, if we code the data, so instead of having x and y, we have capital X and capital Y, where capital X equals log little x and capital Y equals log little y, then the coded data, x and y, will have a linear relationship between them because of this argument here, okay? If I take logs on both sides of this equation here can be written like this, and that equation there shows a linear relationship between capital X and capital Y if capital X is this and if capital Y is this, okay? So this is the same idea as coding data as we met in the first year textbook. Instead of this x data, we're going to take log of that number, and that's what's going to go here, log of this number, and that's what's going to go here, log of this number, that's what's going to go here, and then the same thing, log of this number, and that goes there, log of this number, log of this number. And then I will have a correlation between x and y, and then I can use, instead of looking at these two rows in my table, I can look at these two rows in my table and apply everything that I'm about to learn in section 1.2 and 1.3, or maybe I can look at these two and have a regression line, or any of those things that we can do with correlation. Any of that mathematical apparatus will work on these two, because if these two, little x and little y, have this kind of relationship, these two, big X and big Y, have a linear relationship, and therefore we can look for correlations and all that sort of thing, okay? Now, what you're probably noticing is, well, that's fine, as long as little x and little y have got this sort of relationship. Two questions are probably popping into your head. First of all, how do I know whether they've got this kind of relationship or not? Well, the answer to that one is, if we suspect that little x and little y have this sort of relationship to each other, y is something to do with x squared, or y is something to do with x cubed, or y is something to do with x to the power of 4, then I could do this coding, and I could look for a correlation between big X and big Y, and if there is a linear correlation between big X and big Y, then little x and little y did have this sort of relationship. So there's one answer. And the other question that I hope is occurring to you is, well, that's fine, but what if x and y are related, they follow some sort of curve, but it's not y equals a times x to the power of n, it's some other sort of thing. Now the answer to that is that for the moment, we're going to look at two different possible curves that x and y can follow. There's the first one, and that's what we've just done, and here's the second one. If x and y are related in another kind of way, we're not going to deal with it for the moment, but the answer is you'd have to think of a clever coding, which would mean that if you're starting off with your little x and your little y, what coding could you use so that your big X and your big Y have a linear relationship, depending on the maths of the formula that you think like links little x and little y, okay? So we're going to get two answers for the moment. So we'll use the same trick. If my little y is, I think, k times b to the power of x, well, looking at this equation, taking logs on both sides, log y equals, and I'm just going to go straight there this time. Well, actually, let's not. Let's say log k. You can always fast forward this bit if you think this is straightforward, but using my log rules, we're timesing k and b to the power of x, so I can change that to a plus here, and log, I'll make my g's look like g's, shall I? Plus x times log b, okay? So in this case, if instead of log y I had a y, and instead of x I had an x, this is log k plus x times log b. So there's my straight line again. This is a constant, so I could replace that with c. This is a constant, so I could replace that with m. Y equals mx plus c. Okay? So in this case, if you've got your little x and your little y in your table and all the data for little x there, all the data for little y there, if you think little x and little y follow this kind of relationship, then if you change them into big X, which is going to be the same as little x, and big Y, which is going to be, so the big X column, the big X row rather, is just exactly the same data as the little x data. But the big Y is going to be log of little y. And just to point it out, this is where it says it in the textbook. Then what you get is this big X and this big Y have a linear relationship between them. And that would mean that this little x and this little y have this sort of relationship, an exponential relationship between them, okay? Now, the last thing to say on this is that from the look of the questions, and if I'm honest with you, this was not on the old A-level syllabus, and this is the first year I've taught this particular part of this course, so it's not impossible I'm not entirely right here, but from looking through the questions, it looks to me like we don't need to remember all of those details. What we need to get our head around is they will give us the coding. So exercise 1A here, look, data are coded using this coding to give a linear relationship. We need to remember that that coding links back to this kind of equation. We don't necessarily need to remember all of the details of kind of exactly why it works and using the log rules and so on, as long as we can remember that it goes back to this sort of thing. So state whether the relationship between little y and little x is of which of these forms is it. Well, you need to remember that that particular coding goes with this sort of relationship between little x and little y. So we don't need to remember all the derivation of this, but we need to remember the consequences of it, okay? And that, I think, is everything you need to be able to do exercise 1A.